Okay, in this presentation, we are going to talk about some important applications of probability in biostatistics. Now, actually, this presentation is not from the textbook. It is an independent presentation. And the authors are mentioned right here. Now let's get to the next slide and see what we need to learn. First of all, okay, performance characteristics of a test. Test means like a medical test. Like nowadays you have test for something called HbA1c, like for diabetes. Then you have pregnancy tests. Then you have tests for different kinds of cancer, like PSA for the prostate cancer. Now, so once you're given a test, there are certain performance measures that you use to see how effective the test is. Okay, so now actually sensitivity and specificity are very important features that are used to see how effective a test is. Let's not worry about choice of a threshold. Okay, that's kind of biological in nature. So I don't know enough about how to even set the threshold, but let's talk about sensitivity and specificity. Okay, and then also once you're given a test, the performance of a particular test in a population also matters. Okay, I mean, like once you're like something like TB, it has a test for TB. The public, from a public health point of view, it's important to know whether that test is really detecting true TB patients and then rejecting patients who do not have TB. So stuff like that are also important. So the performance of a test, matters even when you talk in terms of an entire population or a community. Okay, all right then. So for those, the measures will be positive predictive value, negative predictive value, and then the disease prevalence. Of course, this does not talk about the performance of a test, but these are important things that you need to understand when you talk about disease, how a disease is spreading in a community. Okay, all right. Okay, so let's go to the next slide. um okay, so here's a picture. Like if you have a disease, not that many will usually get a disease, right? I mean, it's only a few of them will get it. And then so the reds are affected and the blues are non-affected. All right, so this is how the diagram or representation of a population may look like. Okay, so next, go to the next one. um Now, a perfect diagnostic test will identify only the red ones, not not any blue ones at all. But that is, that's hard to even expect, right? Because no test is perfect. So, but what you should try to do is try as much as possible to get a test which will identify most number of reds and then reject the blues. Okay, all right. So let's go to the next one. um, Yeah, so as I said, in reality, tests are not perfect. So a test may detect most of the reds but leave out a few. Here it's two. And of course, may include some of the non-affected ones as well. Okay, so that's how it is. But you must try as much as possible to include only the red ones. You need to have the circle like this, right? That. All right. Okay, so then let's go to the next one. Now, first of all, sensitivity of a test. The sensitivity of a test is the ability of the test to identify correctly the affected individuals. Okay, so because now see, you will have a whole lot of affected persons. Now, when you do the test, some may come positive out of this affected, some may come negative. See, now this is bad. This is saying that the test is not good. So if the false negative, abbreviated as FNs, This should be as small as much as possible for a test to be effective, right? So if you take the subgroup of affected persons and then if they are subjected to a test, we will have the true positives and the false negatives. So for the test to be sensitive, the true positives should be really, really high. If there are no false negatives, then this test is 100% effective. Okay. Now, how do you measure sensitivity? You can guess. It is the proportion of true positives out of the total affected. Total affected will be the sum of these, and then you will calculate to see the proportion who were truly positive. Okay, all right, so that is sensitivity. Now, here's an example. So, true positives were 148. There were altogether 150 patients with acute Q fever. And then, of course, the sensitivity works out to be 148 over 150, 98.7%. Pretty high, pretty good, right? So, I'll just give you a minute to sort of understand this. So, okay, so this is how we find sensitivity. It's really simple and it agrees with our common sense. This is the formula. Actually, rather than memorizing the formula, of course you don't have to memorize for the exam because it's all open book. But I think you need to understand the intuitive, reasoning behind the formula. Okay, so this is how you get it. All right, and then let's go to the next slide. Um, Okay, so what factors influence sensitivity? Of course, the nature of the pathogens certainly affect because the test how the test is going to be effective depends on the nature of the pathogens. Are the certain pathogens in the disease sensitive to the test? That's one thing. Of course, that is certainly a yes. Now, the characteristics of the non-affected persons, I don't think so. Because see, what is sensitivity after all? It is a conditional probability. Because you are restricting your attention only to those who have the disease. So this is a conditional. See, it is a conditional probability. Conditioned conditioned by the event or the characteristic that that the what you consider are people who have the disease. Okay, that means affected persons. So this is the conditioning event. So the non-affected persons do not play a role in here. Okay, so in other words, you are just forgetting about them from the entire population. You are considering only them. Okay, so now, prevalence of the disease. Now, even that has plays no role. Now, we still do not know exactly what the prevalence is, but you may be knowing a rough idea. Prevalence is how much spread out the disease is in the entire community. Now, even that does not play a role because you are selecting the people who have the disease. Okay, so that also does not play a role in sensitivity. Okay, all right then. So let's go to the next one. Now, this is the other feature or the characteristic that is important to measure the effectiveness of a test: specificity. Specificity means, it is a measure of, how effectively the test is rejecting those who do not have the disease or those who are not affected. Okay, so if you have the non-affected persons, now that subgroup, now this is subgroup, from that subgroup you will have, now they will be given the test to them. There will be a good number of false positives and also true negatives, right? Now specificity means the proportion of true negatives out of the entire non-affected persons, right? So this is the specificity formula. Okay, so in other words, how much are you rejecting, how many are you rejecting? These are the true negatives. Okay. Okay, so now let's go to the next and then next slide. So here's how you calculate the specificity in a example. So you have altogether 200 who are not affected, and then 190 came out to be truly negative. Okay, and then there were 10 who the test result said positive. So this is bad. Okay, but 190 over 200 gave a 95% specificity. Okay, so it's pretty decent, but anyway, these 10 individuals had to worry for no reason because their test came positive, but they don't have the fever, right? Okay, all right then. So let's go to the next slide. Okay, so here they have just given the layout. So if you sort of have like a 2 by 2 table, you have the disease status, yes or no, and the test result status, plus or minus. So to get the sensitivity, you take the proportion of TP um, divided by the total number of affected, which is TP plus Fn. And then to get the specificity, you have to take the proportion of true negatives out of all those who were not affected. Okay. So now, for a test to be effective, both sensitivity and specificity should be high, right? You guys agree with that? Okay, I think there's a specificity. I think there's a typo in here. Specific. Okay. Yeah, now actually, let's think about something like coughing. Coughing. I mean, coughing is of course a symptom. It's an informal test. So if you think of coughing is like you will think of coughing to be a symptom of lung cancer. How good is it? It may not be really a good measure because there will be many without lung cancer who cough quite a lot. They are actually this, right? They don't have lung cancer, but they will be coughing. The test is actually coughing, right? So if this quantity is very high, the specificity is going to be low. Okay, all right. Okay, so to whom does sensitivity and specificity matters? To lab specialists, right? Because they are only developing the test, so they need to understand or figure out how effective their test is. Of course, in addition, the test would be a useful tool for clinicians and social workers as well. So let's see how the test, how a medical test is viewed in terms of a population. All right. Okay. So let's look in here. So if you take the entire population, you will have affected individuals, then non-affected. Remember this picture, and then how do you calculate the prevalence of a disease? So, I mean, again, go by your intuition. You will take the total number of affected and divide by the total number of people in the population. So it's like A plus C divided by this entire quantity A plus C plus B plus D, right? So that is how you get the prevalence. It's really, really straightforward and then very much agrees with our common sense, okay? Now, this is also an important measure to remember, the prevalence of a disease, okay? Now, now prevalence has nothing to do with a specific test. It is something that is happening in the community because the disease has spread, right? The test has nothing to do with the prevalence. Test does not influence the prevalence, right? Prevalence does not influence the test either. Like, well, I mean, it doesn't. Of course, if the prevalence is high, you will have um, excuse me. Um, yeah, yeah. If the prevalence is high, let's see. If the prevalence is high, even then, you are restricting yourself when you calculate sensitivity to people who are affected. So that may not play a role. Okay. Um, Okay, so let's go to the next slide. Yeah, okay. Yeah, okay. Now, when you talk about a test, how is it is going to be functional in the entire population, you talk about something called the predictive value of a positive test. Okay, so in fact, this that has the abbreviation PPV. It is positive predictive value. PPV stands for positive predictive value, right? Actually speaking, it should be. Um, I think it should be written as positive predictive value of a test. Just a minute, please. Positive predictive value of a test. Now, now this is kind of like the opposite. See, it is like, okay, that is the probability that a individual who is tested positive indeed has the disease. So look, now the roles have changed, right? The events. Remember sensitivity? Sensitivity is the other way around. Sensitivity, now look in here, it is the probability that the test is positive given that a person, for a person who has the disease. Okay. PPV is the other way around. Okay. So now what it is saying is if you are tested positive, do you really have the disease? Now that is important when you talk about entire population, because if so many people come with the test positive, if the test is not going to be good enough, it's not going to be predictive effectively, maybe there will be unnecessary alarm, right? So the PPV should be high, for a test to be effective. All right. Okay, so let's go to the next one. So how do you calculate the PPV? Now, it is actually now there will be altogether how many are affected, A plus C. Wait a minute, there's a mistake. A plus C, it should be, so this should be C, A plus C. Out of the A plus C, how many came out positive? That will be the PPV. Okay, all right then. Let's go to the next one. Mm, Now, this says, okay, what are the factors which influence the positive predictive value? Of course, sensitivity, because, we in fact saw the connection between sensitivity and then also the specificity. The more the test is specific, there will be more, um, more it will be negative for non-affected persons. And then also the prevalence plays a role, because see in here, look, you are choosing the people who have the disease, so prevalence plays a role. If the prevalence is high, you will have more who have the disease, right? So then your subpopulation is going to be much higher. So prevalence plays a role in here. Okay, all right. Um, so now prevalence, of course, now in in this presentation, prevalence is defined formally here. I mean, intuitively it is clear. It's a number of cases of the disease um, in the population at a given time. Okay, it's either expressed as a proportion or a percentage. Okay. Now prevalence can be changing even from one day to the other. Okay. Okay, now predictive value of a negative test. I think it should be negative predictive value. Oh, negative, let's see, I think I made a mistake in here. Negative predictive value of a test is, you can see is sort of like an opposite. Um, is the probability that an individual testing negative is truly non-affected. So here again, look, compared to the specificity formula, okay, the conditioned event is you know is reversed or interchanged. Okay, so so here's how you get the NPV. I should put an equal here. All right. And then let's go to the next slide to see how you calculate it. So you will have altogether you will have C plus D people who are negative. The test has is telling C plus D people are negative. Out of them, how many are truly not affected? D. So D over C plus D would be the NPV value. Okay. All right then. Let's go. Let's go to see what factors influences the sensitivity, specificity, and again the prevalence. Okay, so because see you are choosing um, be- based on the prevalence only. You know you will have excuse me. Yeah, so now, yeah, even the prevalence, of course, matters in here. If you have a low prevalence situation, then the chance for there will be a chance for more negatives, and then the test will pick up more true negatives, right? Okay, so now let's go to the next slide. Um, so here's how the negative predictive value and prevalence vary for different sensitivity values. Okay, so because see NPV depends on sensitivity also, not only prevalence. So for different sensitivity values, NPV behaves this way, the trend is this way. All right. Okay, so now so far what we have learned: sensitivity, specificity, prevalence, um, positive predictive value PPV, and negative predictive value NPV. Okay, so those are the things that we have learned so far. I mean, and then now relation between some of the things that we have studied so far. Actually, this is a little bit mathematical. I think you can see how these numbers have come about. I really do not expect you to know this thoroughly, but if you are interested, if you are math oriented, or if you like the math side of biostatistics, pay attention to this. Otherwise, you don't have to worry too much about it. And then now see, if you take like the total number of, yes, that means total number of people who are affected. Now that is actually prevalence. Of course, remember that these are given in terms of proportions rather than the counts. Okay, see, the proportion will be typically you will have a count here and you divide it by the total number that you have right here, like if you have a regular table. So, but this is like of the proportion. Okay, uh, now I don't think you need to know this. In fact, the slide gives the formulas in terms of that picture, how to calculate PPV and how to calculate NPV. But, rather than knowing this, you can certainly have this in your formula sheet. It's just a matter of knowing what these stand for. That is what is needed to calculate PPV and NPV. Okay. Um, so actually, PPV is the proportion of true positives, right? And NPV would be the proportion of true negatives. That's pretty much what you need to remember, and it is intuitively clear, right? Um, Okay, so now let's go to the next one. Yeah, it's the same idea. And then see, now these formulas, if you are math oriented, you can see these formulas are helpful in understanding relationships. Now look, here the specificity is in the denominator. So typically when you have something in the denominator, as it increases, this should be increasing, decreasing rather. But the fact that it is a negative means that both these go in the same direction. So that's why they say, okay, as specificity increases, so does PPV. Okay, so they both, increase in the same direction. They both increase at the same time. Okay, the same is true for sensitivity and NPV. Okay. All right, let's yeah, the same ideas here, and then let's go to the next one. Okay, now do you think you can, if you can get these numbers, that means you know a good bit of biostatistical formulas. I mean, they are pretty simple, as we realized. Can you check all these numbers? How you got prevalence to be 0.5? How you got sensitivity to be 98%? So spend about 5 minutes and then go over this, and then see. You can pause the audio presentation and then look to see whether you get these answers. I checked them myself. They are correct. Okay, let's go to the next one. Yeah, again, it's another example. So again, you can try, to see whether you get these answers. Okay, now, to whom do predictive values matter? Look at the denominators. So if I go back, actually, let's see, maybe, yeah, somewhere here I have mentioned, yeah, the denominators are those who are tested positive or those who are negative. See, if you look, let me go to the slide, the previous slide. That okay. So here, look, this is the number of positives, those who tested positive, and this is the number who came out negative. So actually, these are the two things that go in the denominators for the predictive values, the positive one and the negative ones. So these are the number who came positive, these are the number who came negative. Now for for them certainly predictive value, let's see, I need to go to that slide, matters, because if you are tested positive, of course you will worry, and then you will say, okay, is that test good? Is that test good for prediction? And at the same time, even if you are negative, is that test accurate enough? Okay, in that sense, it matters to people who belong to either positive or negative. Now, then also to clinicians. Now, for a clinician, see, there's a difference between a clinician and epidemiologist, from healthcare point of view. The clinician is interested in his or her patient, right? So uh, they are it is their interest, which matters to clinicians. Okay, so if there's a person, if there's a patient of a clinician, and then that person comes up with a positive result, so the question comes up, okay, is that person really sick? So just the fact that the test is positive will have a very high chance that the person is sick if the PPV value is high. Okay, so for clinicians it matters at an individual level, and at the same time for epidemiologists who are interested in the community at large, certainly it matters as well. If the PPV is very high, is it really corresponding to the true proportion of patients? Uh, so So the summary, so what we pretty much studied in here is given in this summary. You can go over it. Now, as the math or the stat part goes, this is pretty straightforward. We are talking about really proportions, and then we are really using the very basics of probability. And then if you do a couple of problems, you should be okay with this. Now, of course, even though the math is simple, these ideas are really, really important if you are going to be a physician or a social worker or lab scientist or any person who is into healthcare. Okay. So this is an interesting presentation, and then also it is useful. So take some time to go over it. Okay. All right. Take care.